Thank you, Kirchi, for the very nice introduction. And it's always a pleasure to speak in one's home place. So today I will tell you about new tests of quantum mechanics with atoms. This is the first time that I give this talk. I've given parts of it, so some of it may be a little bit rusty. Please bear with me. I put a picture here of the clock in the UT Tower because at least part of my talk will be about clocks, though not those kind of clocks, a little more advanced. This talk has since it's lunchtime, roughly, I thought I'd offer you a menu with three courses. The first course will be, does 1 + 2 = 3 in atomic clocks? Second course is, do atoms age? ? And third and last course is putting gravity in context. And the common theme will be precision measurement in atomic physics. So we will start with this one. And this part of the talk was inspired by Steven Weinberg. So I want to start out by remembering him. Known, of course, to most people here. Steven Weinberg died in July 23rd of 2021 at age 88. He spent most of his career actually in Texas, came here in the early 80s, spent about 40 years on the faculty, and I was he was my advisor and mentor and friend, and is very greatly missed. So, and you can read more about the life of Steven Weinberg in the obituary that I wrote for Physics Today. And also I have a talk on YouTube. If you can't find these, I'll be happy to send you the links. So just email me, please. So about this story today starts about 6.5 years ago. I wrote it down in my notebook, so I know that the exact date was June 10th of 2016. I don't remember what time, but he called me up out of the blue and told me, I have some questions about atomic clocks. And after my initial response, I told him, sure, I'll be happy to talk to you about this. And what at that point, Steve shared with me an abstract that he wrote. Entitled The Lindblad Decoherence in Atomic Clocks. The abstract says, this is a very short abstract, it is shown how possible corrections to ordinary quantum mechanics described by the Lindblad equation might be detected by exploiting the great precision of atomic clocks. And I love the opening sentence of the paper, because it says, in searching for an interpretation of quantum mechanics, we seem to be faced with nothing but bad choices. So Steven Weinberg, like many physicists, was very unhappy with the interpretation of quantum mechanics in terms of the wave function and collapse, the Copenhagen interpretation, and even less happy with the many worlds interpretation of quantum mechanics, partly because it had no predictive power. It was just kind of spooky, put in by hand. And he felt that there should be some real rigorous basis for incorporating the environment in quantum mechanics, because all quantum systems interact at some level with the environment. There's no perfectly isolated system. What he thought is that in his extended theory, which had to be compatible with ordinary quantum mechanics, that transitions in atoms should reflect this entanglement with the environment. And what that would amount to is a shift in a frequency of a transition. The problem is if you say, let's measure that, and you want to, let's say, measure an atomic clock, you wouldn't know what is the kind of the quantum prediction versus what is his extended theory would say. I guess you could rely on calculation, but there's no one experiment that you could do. So Steve argued that what if we could find an atom that had the following properties? It had 3 levels called an A, B, and C. And you have transitions associated with them. So from A to B, we'll call that 1. From B to C, call that 2. And from A to C, call that 3. Now, what Steve argued is that perhaps 1 + 2 does not exactly equal 3. Maybe is 3 plus or minus epsilon. And that was, in a nutshell, what he was proposing. The rest of the paper kind of goes into more details. But what he wanted to know, what he asked me specifically, is there an experimental system where this can be tested? I spent a lot of time thinking about it and read the literature, and to my disappointment, I couldn't find anything. It really was very sad that I couldn't identify any system where you could talk about it in theory, but 3 connected clock transitions just didn't seem to exist, at least at the time. So Steve told me, don't worry about it, I'll ask David Wineland. Oh, that, yeah. Okay, so he asked David Wineland, who was also my postdoc advisor, and Dave thought about it for some time and came back to him with the same answer. He couldn't find anything. Well, I have to say that made me feel a little bit better. Right? And but it didn't make Steve feel better. And the paper got published eventually. It was kind of he told me it was kind of a painful process, arguing with referees. And one of their complaints was that there was no physical system in mind. And you can talk about it in abstract, but that was kind of the objection. The paper got published. It really didn't get noticed by the community, especially the atomic physics community. Very few citations. And Steve and I would meet regularly for lunch, and he never brought it up again. But I think it was kind of a sore spot, and always felt like this was unfinished work. But of course, if this could be tested, and it gave a shift where 1 + 2 is not exactly equal 3, this would require reformulation of quantum mechanics. So it's extremely important. So after his passing, and when I was working on the obituary for Steve, it gave me the opportunity to reread many of his older papers, specifically the one from 2016. And I revisited that paper and started looking into it again. And meanwhile, some work had been done in those intervening years that I wasn't aware of. And I got together with 2 friends and colleagues, one of them, Jerry Gilbert, who's also a former Steve student, who's now a fellow of the MITRE Corporation working on quantum computing. I hope to bring him next fall to visit. The other is Dima Butker, a very well-known AMO physicist who was for many years at UC Berkeley and now chair professor in University of Mainz in Germany. And together, combining some recent experimental results and some new ideas, we came up with something. First of all, the first thing was we identified that there are actually current limits, but they're not very good. And specifically 2 alkaline earths, radium and calcium, a singly ionized radium and singly ionized calcium. These roughly, that's the energy level structure for both. Both atoms share the very similar structure of alkaline earths. The problem is that not all those 3 connected transitions are clock transitions. So you don't have much accuracy. At least one of, if not 2 of the legs were electric dipole allowed transitions. So they just weren't very accurate. So that was part of the problem. And that's sort of the problem that I recognized, and I think Dave Wineland recognized. We couldn't find true clock transitions, which would take into account, take advantage of the extraordinary accuracy that atomic clocks have these days.
So
some of you,
Mark, what do you mean by clock transitions?
a clock transition just means it is a forbidden transition that has a very long lifetime, so a very high Q. That's all. And to be a good clock transition, you also want it to be fairly insensitive to external fields, so electric fields, black body radiation, all the things that might shift a clock frequency. And that is part of what we call modern day metrology. We had a wonderful talk in the fall by Jun Yi from JILA, who presented the state of the art with the strontium lattice clock, and they are already, I think, at part 10 to the 19, and very soon they'll be a part 10 to the 20. We don't measure anything better than that, than clock frequencies. So that was Steve's motivation, first of all, that with this incredible accuracy, we can search possibly for new physics. Yes.
Is the accuracy, as you mentioned, of both 1 and 2 and 3 also an issue in this algebra?
Well, you want to have all 3, 1, 2, and 3, each of them be a separate clock transition, because then you could test that the sum of 1 + 2 = 3 to an accuracy set by, I mean, that it'll be limited by the weakest of the three. And so generally, if you want to set a stringent limit on that sum, you want all three to be the best atomic clocks you can find. Right? So what we found, in short, is we identified one case. And actually, since we did this, other people have come up with other cases. So it's kind of nice. It kind of, in a way, opened the floodgates, because then once you kind of knew what you were looking for, it allowed you to find other. But the one we like in particular is ytterbium. That's one of my favorite atoms of all times, because partly because we are very involved in production of a medical isotope. This is a stable isotope of ytterbium, ytterbium-176, which we're doing right now at a nonprofit foundation called the Pointsman Foundation. So we don't do atomic clocks. That's left for people like Junyi or at NIST. Although NIST lattice clock is about as good as the strontium lattice clock that Junyi told us about. Just a word about the Pointsman Foundation. I won't say much more. This would be a separate talk, but I just say a word since I mentioned it. You can look up our activities at www.pointsman.org. This is a nonprofit entity that I started about 5 years ago. It has a board of directors, mostly medical doctors. And we are working on advances in the physical sciences to benefit humanity. We have a private lab in Austin where we're actually producing medical isotopes, which will be used in cancer therapy, prevention of iron deficiency, et cetera. And you can read some of those projects. So that's why we are very much into ytterbium. But back to the spectroscopy, what we found were three bona fide clock transitions. And this is the Grotrian diagram, not shown to scale, of ytterbium. Probably doesn't mean a whole lot to you. It kind of is like the alkaline earths in that it has a 0 spin in the ground state, and then it has a triplet p state. But looking at the energy levels, ytterbium-1 means neutral ytterbium. We have the ground state is the 1s0, and then this state, the 3p0 state, has a lifetime of 20 seconds. That is now the standard clock transition at 578 nanometers for neutral ytterbium, which has extraordinary accuracy. But this one was not known in 2016. That was the missing link. And this one is in the infrared, was measured in 2018. And then we found how to complete the kind of the diagram in this way. We have A, B, and C, as I showed before. This is A to B, which I did. 1 is 578 nanometers, green. Then there's 862 from 1 to 3 is actually a 2-photon transition. That was what we had to go to. And then a single photon clock is 1695. Now, 2-photon transitions are not ideal, but the 1s to 2s in hydrogen, which is a very high accuracy, still is a 2-photon clock, because it's at 243 nanometers, twice the wavelength of Lyman alpha, roughly. So it's certainly acceptable. People would agree that that is a clock transition. So with that, we can now ask, does 1 + 2 = 3? And we don't know the answer yet, but we did publish a paper. It actually was also hard to get published, I have to say. We argued a lot with the referees. Some said this is really interesting. Others said this is trivial. You know, it's the usual fight. But eventually we got it published. It was kind of annoying also that the editors would not let us put the original title, which was "Does 1 + 2 = 3?" So we had to put it in this kind of boring title here. The other thing is we wanted to dedicate the paper to memory of Steven Weinberg and say, we don't do that. So this is what they did allow us to say. We were grateful to the late Steven Weinberg for discussions about this topic over several years, the memory of which inspired this work. A little awkward way to say it, but in a way, I think what we feel collectively is that maybe this is the best tribute to him, much more than writing an obituary, which is kind of, required. But I think he would be pleased, and he would be even more pleased if these experiments actually turn out to be true. Now, we don't know yet. But I will say, since our paper was published, even since the preprint came out, we've had a lot of interest by the AMO community, and I know of several experiments, not just in ytterbium, but other atoms. Meanwhile, people started thinking and pointing out you could do it here and you could do it here. So there's now several test beds for this idea, and the experiments are in progress. So we will know. I mean, I think one option is it'll just be another null experiment, that we won't be able to say that 1 + 2 = 3. We might be able to say here's within our experimental limits, this is the best we can say. If someone does measure with something that is not equal to 3, this will be a big deal. So I would just say stay tuned. But interesting kind of footnote to. I sort of viewed it as an unfinished paper by Steve Weinberg, and it felt good to at least come out with this, and so we'll see. But all right. Any questions?
If 1 + 2 is not equal to 3, what exactly will have to be modified in quantum mechanics?
Well,
Repeat the question.
if the question is if 1 + 2 does not equal 3, what would have to be modified in quantum mechanics? So standard quantum mechanics would not predict that. So you need some extended theory, and one possibility is the Lindblad equation that Steve Weinberg proposed. It might not be the only one, and so I think one would have to see. And the part of the problem is that in his paper he couldn't actually give even an estimate of what the size of the effect would be. So there was no guidance to say what it could be. So we really have to just go by experimental constraints and say this is what it is. So it'll either be it's less than something, or if it's seen, then I don't know, then there'll be a value, and then we'll have to go back to the theorists and see what they say about it. Okay, other question?
Adam Christensen, what's a typical experiment to test if a given transition is a clock transition?
Well, there's no hard and fast rule, but generally one looks for a transition that is forbidden, so not electric dipole allowed, usually electric quadrupole or magnetic dipole, so very long lifetime. One looks for other properties that are nice for clock transition. For example, immunity to external magnetic fields or electric fields. Electric fields can come about with stray fields, or just black body radiation causes there's an electric field of the black body surrounding us. And so there are numerous candidates for the best clocks. That was kind of there's been big breakthroughs in atomic clocks. And for example, the lattice clocks, they are with neutral atoms. The other competing platform for atomic clocks are singly trapped ions, and they have some their own advantages, but typically they have much lower signal to noise, so they take longer. You can't get as good a measurement in a short time. So the lattice, they're kind of competing, but there is a large community of people working on atomic clocks around the world. A lot of it's being done at national labs like NIST. Juni is at NIST, and actually he's at NIST. Gilla is part of NIST. So typically university groups don't do that as much because I guess it's harder for students to get a lot of publications doing high precision atomic clocks, and it's gotten very, very sophisticated. All right, other questions before I move on? Yeah.
What factors would influence the transitions to resistance to outside field?
What factors?
Well, you said some transitions are more resistant to like an external magnetic field, like for instance. What plays into that?
Well, for example, you like something where when you have a clock transition, you're driving between two levels. So, for example, if the levels shift the same way, then the difference between them is canceled. So that makes them kind of insensitive. So that's one thing. That's actually what allows you to hold the atoms in an optical lattice. That's the so-called magic wavelength optical lattice, is because the two levels do shift, but turns out that by choosing the right wavelength, they shift exactly the same way. So the clock frequency is insensitive to that. Okay, let me move on if there's no more questions. So second topic is, do atoms age? What do I mean by that? All right, so I borrowed this picture, which we all, we all can relate to. We are somewhere, beyond this stage, and some of us are approaching more of this stage, but not quite. And so aging or the process of increase of entropy is something that we are very familiar with, certainly of the macroscopic world. But it is not usually thought of in a microscopic world, because we all learn in quantum mechanics that an atom is immutable. Like if you have a hydrogen atom, you're taught that the hydrogen atom just exists. It was born after the Big Bang and it just exists. We don't know how old it is. I mean, that's all we can say. We can't say this hydrogen atom is older than that hydrogen atom. But in fact, the idea that there could be something that you could measure in an atom, and the best thing that we can measure is a clock transition. Could it vary in time? And there's been a lot of interest in the last few years in the idea that there might be a time variation of the fundamental constants. And so I don't know when this became fashionable, but it is fashionable, and it's kind of a topic of a lot of searches. To date, they're all null searches. And part of the problem, I think, there's no really strong there's no strong theory behind it. It's just to say that if we have these exquisite atomic clocks, let's search, because we can search very well to see if clock frequency, or especially if you're measuring relative clock frequencies, if it is changing in time. Yeah.
The first ideas were in the 30s, early 30s, Dirac and among others. And we actually published a paper where we were looking for weak interaction dependence and periodicity of it in some interactions. So it's actually it's a field that is moving.
Okay, maybe you could get me some references. That would be great. Yeah. So the question that I want to pose today is a little bit different, but it's something that has been on my mind for a long time, because normally we think of an atom as being immutable, but the exception to that is radioactive atoms, because they clearly are born. They're born in some process like a nuclear reactor, where by neutron capture, or in a cyclotron, or where an atom undergoes transmutation and becomes a different element. So we can call that the birth, and then when it decays, we can call that death. And there's a half-life associated with the atom. And the question is, which I just have wondered about for a long time, is could there be some hidden variable that is in the nucleus that you could probe with the clock transition? Because the clock is extremely sensitive to any effect. Anything happening in the nucleus actually will affect it. So, when you're getting to parts in 10 to the 20, very, very small effects could be significant. But I never dared write a paper about this because it would sound too crazy. But somehow, I think through Dima Butker, he hooked me up with these two theorists. We're delighted to meet them. And they actually had a theory. One of them is Surjit Rajendran, and the other is David Kaplan, quite well-known theorists, elementary particle theorists now at Johns Hopkins University. And it turns out that they had actually a theory which had to do with the fact that a unstable atom is actually getting entangled with the environment, and that entanglement would lead to a change in a frequency. But now, that's not to say that this is the only theory, but at least it gives it some credibility. I could hide behind that and say, okay, the theorists say this is possible. And I would argue that quantum mechanics is one of the best theories that we have, that it certainly has passed all the tests to date. But it's interesting if you can come up with an experimental system or proposal that has not been tested experimentally. And that's, as far as I know, a clock of a radioactive atom, where now you could really control the half-life. So we're not talking about comparing the age of the universe, but we can talk in days or weeks or a month, on kind of human timescales when something dramatic is happening. But this would be clearly outside of standard quantum mechanics. So we published a paper, And I have to say, this paper was so easy to publish. I think the trick is that you take out of the title the REV. That actually helps a lot, first of all. And secondly, the authors, the editors let us keep our title, so we were happy with that. You know, so anyway, it got published, and also, yes,
Did you mention in this paper Freshbach and Jenkins?
I don't remember.
You know what I'm referring to, the periodicity of the beta decay?
No. You'll have to educate me on that. Please, really, please do. So they have a prediction about.
Well, they have a very wacky idea of impact of the sun on.
Oh.
On the weak decay,
Okay.
which is somewhat ad hoc.
do-
It is completely.
The sun, you mean by neutrino flux? Oh,
No,
Ephraim,
it's-
you're talking about Fishbach, not Fishbach. I thought Herman Fishbach. You mean Ephraim Fishbach?
Yes.
Oh, yeah. I spoke to him about that. I think it's, I don't know if it's wacky or not, but he showed me the data. I visited Purdue before the pandemic. I gave a colloquium there, and he showed me the data, and it's totally unconvincing to me. You know, the problem is you get these seasonal effects, and they argue that there's a correlation between the lifetime of the rate of the.
Or it's sun activity.
So, yeah, I don't, at least the experiments did not seem convincing at all to me. You would agree with that? Yeah, so, but here we're not trying to change not looking at the change in the half-life, but we would be looking for something else. We would be measuring a clock frequency.
No, but the wind constant would change, and the coupling constant would change.
Yeah, and maybe that would lead to a clock frequency, but again, you need something on a more controllable time scale, and not, I think, at least maybe they could do a good experiment, but the effects were so tiny that they even claimed it was like 0.5% or something, and right, that it just wasn't convincing. So
Again, I'm not defending.
No.
In fact, they're considered to be.
Right, no. I am familiar with that. Yeah. Okay. But when we think about, you know, where we might test this, so we have several candidates, which we discuss in the paper. The trapped ion case was actually the one that Surjit and David, they prefer because it fits into their theory. And so a natural candidate would be lutetium-177. Coincidentally, that is exactly the radioisotope that we're going to be producing at the Pointsman Foundation. So because we're already producing the stable precursor, ytterbium-176, and our next step will be actually to make lutetium-177. So we will have access to that, and there's a group in Singapore that actually is doing atomic clocks with lutetium right now. Lutetium, I think 176. So they could measure this. It's a beta emitter. Half-life about a little under a week. Radium-223 would be interesting candidates. We don't have any special access to that. Also, radium-224 and 225. Those are shorter lived. Radium-226 is the few thousand-year half-life. That would be too long. But these are shorter lived. When we come to neutral atom clocks, strontium is a good candidate. And when Junyi was here, he and I talked about this a lot, and actually got a lot of enthusiastic support from Jan Hall, who was Junyi's advisor and also a Nobel laureate in physics, who has thought about similar things but never dared to publish it. But he was kind of very excited about this. And we could do strontium-89, which has a half-life of a little over 50 days. We do that by enriching strontium-88, stable strontium-88, irradiating in a reactor, and then extracting with MAGIS with our method, extracting the radioisotope strontium-89. So this is very doable, and now it just has to be done. And so again, I don't have the message right now is stay tuned, right? But it'll be interesting to see. These are the best atomic clocks is right now in the world is strontium. So let's compare strontium-89 to strontium-88 and see if there's a time-dependent clock shift. Okay.
So
Now,
Mark,
yeah.
what precision may be required to compare strontium-88 and 89?
We don't know. We don't know, but because it's never been tested, you know, whatever will be measured will be a huge improvement on what we know today, because it just hasn't been measured.
Wouldn't you'd expect some difference anyway, right?
Oh, there will be an isotope shift for sure.
Yeah.
That's a static, not a time dependent shift. Right. The isotope shift can also be calculated, but it can be measured, yes. And one can measure isotope shifts between different isotopes of strontium, for example.
So, we think radioactive decay is some stochastic process, which is, strange aspect of quantum physics, maybe.
Right.
I guess a conventional expectation would be that the time scale on which you would know this a change in the strontium or change in this fingerprint of strontium would be very short. Right?
Where there is, I mean, the
To do with some nuclear physics time scale.
The-
When can you tell?
well, that's the thing is that no, not in Surjit and David's theory. In their theory, it actually, the shift occurs throughout the half-life, not on a short time scale.
And why? Why?
Because it's evolving and it's getting increasingly, I mean, this is hand waving, you have to read their paper, our paper, but really their original paper on the shift. It has to do with the entanglement that develops over the half-life, over that time scale.
Right.
So it's not a sudden thing.
If so, that's just quantum mechanics, right?
Well, it's not predicted though. I mean, ordinary quantum mechanics, like of decaying atoms, is a quantum jump theory. That an atom in a state exists and then suddenly it makes a quantum jump and it's in another state. So I don't think that is included in standard quantum mechanics.
I guess, you have to think about what's the interaction, right? If it gets entangled, it's getting entangled because of some interaction between.
Well,
atoms.
and I think that's why it was essential for them that it be an ion, because it's sort of a self interaction with its own. It's like a self field interaction. That's
So
roughly
their,
speaking.
so their theory does not predict the value, the magnitude of the shift.
It doesn't predict the magnitude, and it also doesn't predict it for a neutral atom, only for an ion.
And then could you create an environment that have more interaction,
I don't think we can do that. It's not like cavity QED where we can affect, in other words, you can affect radiative properties of atoms by changing boundary conditions. That's called cavity QED. But with nuclear decay, I don't think we can do anything to change the environment that I can think of.
So typically, when you talk about this with cosmologists, they will tell you that the age of the universe and the structure formation is a very strong, very stringent constraint on any changes anywhere. It's constant. Have you considered that?
Well, they again, I have to rely on these theorists, and they claim that there's not that there's really no current constraints on that. But yeah, that's what they say. I mean, I take a more empirical approach to this. This is something we can measure, so let's measure it. So we'll see. Okay, let me move on to one last thing I did want to say about this is that, and this is a bit of a stretch, but if it turns out that there is a time-dependent clock shift, this could actually be even useful, because it would imply that you could actually do radioactive dating with a single isotope. Right now, when we think about dating of isotopes, you always need a pair. You need a reference. You need carbon 12 to 14. It's their ratio that you measure. But if you could measure a clock frequency in a cesium atom, a cesium-137 atoms, and you could say, okay, this cesium-137 has this age. And that's something that we currently can't do. And I would call it nuclear forensics. You may have heard in the news recently that someone lost a little pellet of cesium-137 in Australia. And did anyone see that? And they searched and they actually found it remarkably. But very often there's fission products in the atmosphere, 137 and strontium-90. And it would be interesting if you could actually date them by some property. So this is very, very speculative, but I'm among friends, I hope, so we can think about it together.
But so if the theory is correct and you see the effect, what you're saying is it will be a universal effect. So So.
No, we don't know that. And we don't know if there's going to be a difference between alpha decay and beta decay. We also don't know what would be they make a certain prediction on what so that if there's a time variation, they predict some rate, but in fact, it may not be uniform. In fact, my intuition would say that there might be some chirped effect as you get closer to the edge of the cliff, so to speak. But in other words, if the first thing is, do you see a time-dependent clock in a radioactive atom? But if you can see it, then you can see how does it change in time, and that will tell you a lot more. So.
But for the same atom and the same transition, you expect it to be the same. It's not dependent on the environment.
No. I mean, if we have, in other words, the clock would be measured, it would be independent of anything we can do external. I mean, we can always shift things by external fields, but that would affect any atomic clock. But it doesn't. I'm not including those effects. All right. In the time that's left.
So Mark, just so I'm,
Yeah.
When you say changes, in dating, that implies, not the age of the universe timescales, but much shorter
Right.
timescales, right?
Days to weeks.
Okay. There must be constraints from the cosmology. There
It's
must
a question I'll have to ask my theorist friends, because I don't know of them. But they didn't seem to say, I mean, I don't think we put any constraints in the paper.
supernova.
Yeah, but these are, yeah. But I don't know, it's not changed. I mean, there's still a half-life. It's just that some property, which is a clock frequency, is
I
changing.
understand.
It's a fine,
But you're affecting some fundamental constants that are ingredients of the process.
yeah. All right, so the last topic, which I don't have as much time as I thought, but I will not cover everything, is what I call putting gravity in context.
As a dessert, it should be pudding.
What? What's that?
Probably.
Pudding, oh, pudding gravity, okay. Yeah, I suppose, yeah. It's based on this paper by Richard Howell and co-authors that appeared in 2021, where they make a prediction that you could see something which they call non-Gaussianity as a signature of a quantum theory of gravity. And their scheme that they outlined in the paper was roughly the following. You have a Bose-Einstein condensate, and you could measure its correlations by dropping it, looking at time of flight, and measuring on some sort of camera, and looking at correlations. You could construct through what's called quantum state tomography. You could construct what's so-called Wigner function, and then the prediction was that due to the gravitational gravity interacting with quantum mechanics, you'd get a negative Wigner function, non-Gaussian, as opposed to just a classical Gaussian. So they go into detail in this paper, and you can hear his talk. He posted this talk. You look him up, Richard Howell, Oxford. Just look at his website. I think you can listen to his talk. There's another piece of work, another paper from 2019, which also talks about using atoms for testing gravitational physics. This is paper's entitled SAGE, a proposal for space atomic gravity explorer. It's a large collaboration, so this is actually an experiment that is seeking funding and trying to get started based on satellites where there would be having separated atomic interferometers. The proposed mission, SAGE, has the scientific objective to investigate gravitational waves, dark matter, other fundamental aspects of gravity, as well as the connection between gravitational physics and quantum physics using new quantum sensors, namely optical atomic clocks and atom interferometers on ultra-cold strontium atoms. So this is kind of the motivation that started it. But if you look at both the non-Gaussianity and the SAGE proposal, they have a common thing, and that is they both require a very high flux of a Bose-Einstein condensate, also known as an atom laser. So you would need to have what is called an ultra bright atom laser. So how does one produce an atom laser? It starts from laser cooling and trapping of atoms, and that method that works extremely well can be applied to a certain number of elements in the periodic table. Followed by, so that gets you to about a phase space density of about 10 to the minus 6. And a number of atoms can be quite large, even 10 to the 10 to 10 to the 12 trapped atoms, but a phase space density that's still very far from quantum degeneracy. Then you need another method because laser cooling reaches its limit. The limit has to do with multiple scattering of the laser light, because when the phase space density gets too high, you can't cool anymore. Actually, it causes heating. So there was a method that was invented called evaporative cooling of atoms, and it works. But most people don't like it because you lose about 99.9% of your atoms. It's a very slow process and often doesn't work because you have inelastic collisions that dominate over elastic collisions. And finally, once you reach the sufficiently high phase space density, you can form the Bose-Einstein condensate, and you can couple it out so you can get effectively an atom laser. But interestingly, the current state of the art regarding BEC flux is only about 10 to the 5 atoms per second. So this is a very feeble laser. I mean, there was a lot of hype when people first talked about atom lasers. This is just going to be just like the optical laser. Problem is that this little laser pointer has about 10 to the 16 photons per second, and this has 10 to the 5 atoms per second. So it's extremely feeble. This would be like having a laser pointer that you couldn't even see because it would be so feeble. It would be like 10 femtowatts of laser. So you could call it an atom laser, but it wasn't really useful, and you couldn't do precision measurements with it. So meanwhile, I would say the community as a large, the ultra cold community, has gone towards the other extreme of very small atom number. And we've heard talks in the past about atoms and optical lattices for quantum simulation and quantum computing. They're really dealing with very, very small, like a few atoms to thousands of atoms. And so they don't care about having huge numbers. But now it looks like we have some motivation to really think about how do we make an ultra bright atom laser. Well, again, I'm kind of, I think I was overambitious in my talk, so I won't go through this all. I'll just say that have been working on this problem for a long time. And our starting point was to go back to thinking about the way light interacts with atoms, and to utilize a property of the photon that is not the momentum of the photon, but rather the entropy of the photon. And to do that, we went back to James Clerk Maxwell, who proposed in 1871 his demon. The demon, I'm sure you've all seen this picture, can regulate atoms, or they call it, particles, by opening a trap door, and that way causing these atoms to move, let's say, to side A, and without changing their kinetic energy, thereby reducing the entropy of the cloud. And Maxwell himself talked about it. These are his words. He said, if we conceive of a being whose faculties are so sharpened that he can follow every molecule in its course, such a being whose attributes are essentially as finite as our own would be able to do what is impossible to us. The italics are mine. But he said he thought it might be possible, but then he said it's impossible to us. And I would argue that at least the way it's illustrated in the cartoon is still impossible to us. We can't we don't have a creature, we don't have an experimental ability to monitor in advance the motion of every gas phase particle, atom or molecule, and then open or close a trap door. But it turns out that's not necessary. And I think we were the first to propose this in 2004, asking the question, could we make a one-way wall for atoms? And the idea is, if you have a partition, you have atoms not shown here, could you make a partition in between so that atoms can go one way and not another? And we published a paper on this 2005, so it's already almost 18 years ago. And the key thing is that we had to have a conservative potential and an irreversible process to do that. The irreversible process is something known as optical pumping, which was proposed and implemented by Alfred Kastler. And the idea of optical pumping is that you can use light, and he literally called it cooling with light, optical cooling. But what he meant is not the translational motion of the atoms, but rather their internal state. And he argued that if you have atoms coming out of an oven and they coming out, they are in this case a spin 1. So you have in the ground state +1, 0, and -1, three spins in a magnetic field. And due to selection rules of using the right polarization of light, you could pump them up to the excited state with, and in this case with circularly polarized light, always goes delta M equals +1. And eventually, after several cycles, you would accumulate in, everything would accumulate in the +1 state. If you use the opposite polarization, sigma minus, you'd accumulate in the -1 state. And if you use linear polarization, you pump it into the 0 state. And if you think about it in terms of entropy, this is a 0 entropy state. There's only one state. So you, in that sense, you reduce the entropy of the internal state of the atom. And the way we proposed this was actually quite simple. Imagine we turn on, in this box, we turn on a magnetic field, and we choose an M equals a spin 1. Again, let's consider spin 1 case. So we pump all the atoms to the M equals 0 state initially. I'm not showing the atoms, but imagine they're all in the 0 state. Well, what happens? The answer is nothing, because they can go freely back and forth. They don't see the magnetic field because they're in the M equals 0 state. Okay, everyone with me so far? But now let's turn on a laser, and the laser does optical pumping. So when an atom crosses that laser beam, it gets pumped from the M equals 0 state to the M equals 1 state. Well, what happens? Atoms on this side, they can go through the magnetic field, nothing happens, then they get pumped. But now they're in the +1 state. If they try to come back, they see the magnetic field as a repulsive barrier. So they get bounced back. On this side, if the atoms are moving this way, they first get pumped into the M equals 1, and again, they can't cross the barrier. So if you just wait in this toy model, everything will migrate to the left-hand side and the price that you pay is just the one, roughly a photon recoil or so due to optical pumping. But generally, this is predicted to work. And the proof, of course, is the experiment that we did 3 years later, which proved that, in fact, we can cool atoms and reduce their entropy. We got a factor of 350, not in this paper, in a subsequent paper, in the phase space density, which corresponds to entropy. So this is a big factor. The problem was, so this established that this kind of cooling does work, but it didn't conserve atom number. That was the downside. So it wasn't really useful. Now you could say, what would Maxwell say? Yes.
What portion of atoms was
Question.
What portion of the atom was conserved? We were capturing about 1% of the atoms in those experiments, but those 1%, we increased their phase space by a lot. So that's no good, because we want to conserve all the atoms. Right? What would Maxwell say? Well, I can't go and ask him, but he did write a letter. People actually wrote letters at some time, not emails. But he wrote a letter to his friend Lord Rayleigh in 1870, where he sees, I do not see why even intelligence might not be dispensed with, and the thing made self-acting, allowing all particles going in one direction and stopping those going the other way. And so essentially what he was saying, to interpret, is that if you could make a one-way wall, you don't need to have advanced knowledge, as the cartoon would imply. In fact, the device just works. But behind that, what really is going on, and we actually analyze this, is what really is going on is that as the atom crosses this one-way wall, it does scatter a photon spontaneously, and that photon carries away entropy. You can actually get entropy balance, because the laser beam that causes this is a source of 0 entropy photons, because they're all in the same direction. But when an atom takes that and rescatters it into 4 pi steradians, that has increased the entropy of the photon. And if you do that calculation, you find detailed balance. You find that the entropy of the atoms is going down, but the entropy of the photons is going up. And so you don't violate the second law of thermodynamics. So it's not spooky. You don't need advanced knowledge, but the information actually is there. And this work is now getting kind of old, but there's a review article that I wrote in 2009. It talks about the one-way wall cooling method, but also other methods that we developed to stop atoms magnetically using very large kind of 5 to 10 Tesla pulsed magnetic fields that we use to stop atoms in a supersonic beam. We call that an atomic coil gun, and that works very well. So the combination we call comprehensive control of atomic motion. So it's a new toolbox. And the question is, how does that toolbox compare? Well, first thing we had to fix was we had to, the one-way wall worked perfectly in 1 dimension, but the problem was when you go to 2 and 3 dimensions, that's where you were losing. So the solution was something that we call magneto-optic or MOP cooling. And I'm afraid I don't have time to go through this, so I'll just I'll skip over it. You can read the paper. But the bottom line is that that this method promises to be general, high phase space density, no loss of atoms, at least, and fast, but need an experiment. And so we were funded, in fact, to do this for 3 years and before the pandemic, and we made a lot of progress. What we predicted is that the flux using these methods of cooling, that we could get to an atom laser of 10 to the 11 atoms per second. So this would be a million-fold improvement in the flux of the current state of the art. We haven't gotten there, obviously, but at least putting in what we thought were realistic numbers, that would get us there. And that is what you need to do the experiments that I talked about. So that is kind of where we stand. Now, again, I don't have time to go into this because we're running late, but I'll just say that new ideas have come about in our group, even just last summer. And I'm sort of kicking myself that we didn't think of this earlier, but at least no one else did either. So that's the only consolation. And so we have realistic simulations. And here's the punchline, is that for an alkali atom, the cooling was modest per stage, a factor of 2x compression. And that's partly why the experiment we viewed it as pretty difficult, because it sounds good, a factor of 2x sounds geometrically fast, but if you really include all the factors like expansion, free expansion or other heating effects, it's really not good enough. But what we found is that as you go to higher spin, higher angular momentum atoms in their ground state, chromium has 6, erbium, I'm sorry, what is it, 4? I forget what. Logan, do you remember? 3. And erbium is 6 and dysprosium is 8. So in the case of dysprosium, we almost get to a factor of 15 times compression in 1 dimension in one cycle. Now imagine you do this in 3 dimensions. Just 3 cycles of this MOP cooling should get you a factor of 15 cubed. So very quickly you could get phase space densities that would be very close to degeneracy. You might have to do evaporative cooling at the very end, but that's to remain to be seen. In fact, one really would have to do a quantum analysis of this kind of cooling. But it gives us a lot of optimism, and we just submitted a paper last week or so. It's on the archive, efficient cooling of high angular momentum systems, where we predict that realistically we could take an atom like dysprosium or erbium and very quickly conserve atom number, compress phase space. This would be an alternative to evaporative cooling. It would avoid the problems with evaporative cooling and allow one to get these kind of ultra bright atom number. And with that, I'm coming back to this putting gravity in context. I didn't come up with that title. I'll suggest to the person who made that we replace the T with 2 Ds. Okay, maybe that'll improve our chances with the referees. You never know. So we just submitted, or we submitted a pre-proposal. They had a call for proposals. We submitted a pre-proposal, and actually we were notified recently that we made it through the first round. So we were invited to submit a full proposal, which is due in 2 weeks. So there's no guarantee we get funded, but at least we kind of were inching our way up. And so if we do get funded, then this will allow us to implement MOP cooling, make an ultra bright atom laser, which will be interesting for many reasons, but in particular allow us to make these kind of tests. And so that's where we stand. Now we have to get to work and I have to end my talk so I can get back to proposal writing. And so I'll just end here and thank you for your attention.
Talk. So, any questions from the audience?
Yeah, okay, started. What is the state of the art
For the atom laser?
10⁵ atoms per second,
Okay,
condensed atoms per second.
any more questions? Yes, anyone?
And that's after a lot of effort. That's a many years of effort. I think the weak link in the process really is evaporative cooling. Because it is slow and it is very lossy. So that's the bottleneck. If you could replace evaporative cooling, then that's what we have to offer. There might be other approaches, but so far people have not found it.
Any more questions?
Maybe,
Go ahead.
what's the Landblatt in Stephen Weinberg's paper?
What is the,
Am I saying the name?
let me. Lindblad.
Yeah.
Lindblad.
So that's, doesn't that imagine some kind of environment?
Yes.
So it's sort of like variables or not?
No, I don't think it's hidden. I mean, I think it is, so the paper was actually,
There was an equation of motion somewhere. in this
yeah,
paper.
so it's in his paper, the explanation, but I don't know if he was the first one to, I don't think he was the first to propose this, obviously, known equation, but he was the first to propose a possible observable.
Or what does it mean? What is the generalization of quantum mechanics?
It's to include it incorporates the environment supposedly in a more natural way than just a density matrix.
But, system environment, we believe we can, all follows the rules of quantum mechanics. So
Right.
is it something beyond quantum
I
mechanics?
believe it is.
Some kind of,
It's, yeah.
I was gonna just, same question, how do you distinguish when lighting interaction with your environment versus a complete lighting viewpoint, which is quantum?
Well, I don't believe that this kind of clock shift was predicted in the context of standard quantum mechanics.
if you have an interaction with an environment, it will, always produce some kind of self-energy effect that shifts the frequencies, right?
Well, there is that you can get a broadening, so a lifetime change and presumably a shift.
Yeah.
As well. So but I think it's more than that, because if that were all it is, my understanding is that would lead to a shift of the energy level. But an energy level shift would not lead to 1 + 2 not equal to 3. You would always, that would preserve it. So it's somehow that
There would
it's,
be some correlation between how the different transitions interact with the environment. So
right.
in principle, I think just an ordinary system plus environment, quantum mechanics. 1 + 2 is not equal to 3.
That's never been, yes,
It would be, yeah.
but I don't think that's, I mean,
Okay. Anyway, that's.
To my knowledge, that's not-
I got a better idea now.
From Alex Stram, how do you drive the forbidden optical transitions you talked about?
you drive it. Typically, it's a laser that is turned on for some time. Usually, and there's advanced methods that are used to probe this. For example, what's called the Ramsey method of separated oscillatory fields, where you excite an atom first to a superposition state of the ground and the excited state, and then you let it evolve for some time, and then you complete it with a second pulse. That is kind of a standard methods of probing in an atomic clock. And then you usually in an atomic clock, what you need is you need to be able to detect whether you actually made the clock transition. So you can either do that by having a laser that would scatter from the ground state, or a laser that would scatter to another state from the excited state. So if you see the existence or absence of that scattering, then you know did the atom make the transition or not?
Yes, interesting. And let's thank Mark again. For people who are signing for the make sure you sign the candidacy for the class.
Leaving my office.
I don't know.
Yeah.